last time.
No, it's
No,
It's doubling every single day.
It'll only be $1 that he puts in that day.
Yes, that is true. No, it's not.
No,
Not in
it's
100
not.
days. Anywho, sorry. It is doubling every single day. So day 1, 1 cent. Day 2, 2 cents. Day 3, 4 cents. Day 5, or day 4 would be 8 cents. Day 5 then would be. So every single day he's doubling the amount of money he put in the day previous. Using that information, we're going to answer 2 questions. The first one says, assuming he is not, oh, sorry. No, just kidding. That's part B. If he continues to double the amount set aside each day, I'm going to use AMT for amount. How much will he set aside on the 15th day? There we go. So this is part A. How will I figure out how much money he's putting aside on day 15? Any ideas? Okay, so I have to find R, and I'm going to use it somehow, but how is that really going to help me for the 15th day if I only know the first 3 days? I'm going to use the formula for the nth term, and I'm going to plug 15 in for n. So the formula for the nth term, remember, is A of n equals A of 1 times R to the n minus 1 power. Do I have A1 and R here? Yes, I know how much money he put in on the first day, and I know how it's changing from day to day. So I go ahead and I fill that information in, and I get A of n equals 1 cent, because that's A1, times, if we're doubling, we're multiplying by 2. So my R here is 2, which I will raise to the n minus 1 power.
Doesn't 15 go where the n is?
And then we're going to put 15 where the n is so I can figure out how much he's putting aside on day 15. So we end up with A15 equals 2 to the 14th power, which I can go ahead and plug into my calculator. Molly, what do we get?
1,600. Sorry, 3,384.
What?
Okay, so we get 16,384. Is that dollars or is that cents? That is cents. So if I'm writing this as a dollar amount, I just take the decimal at the end of the 4 and move it 2 places to the left. So then
That's still a lot.
this is equivalent to $163.84. Remember, that's just how much he's putting aside on day 15. That's not how much he's accumulated over that time. So on day 15, he's putting aside $163.84. Any questions on how we got that? So there's a part B to the question. Part B says, assuming he does not run out of money,
See, he is rich.
He's a good
Can we just do day 100 since Marissa thought that was going to be $1?
no. What is the total amount saved at the end of 30 days?
this two examples?
No, this is all one example.
We only did 2 examples today.
Well, actually, I guess we technically have 2 more left after this one, but one's really, really little, so I don't count it. So what is this question asking for?
30 days.
The sum of how much he's put aside for the first 30 days. So what am I going to use to calculate this sum? The SN, or my partial sum formula. You could also individually find out how much you put aside each day for 30 days and add that together, but it's going to take you much longer than just using our partial sum formula. So for, excuse me, for geometric sequence, my partial sum formula is equal to A1 times 1 minus r to the n over 1 minus r. Filling in the information for my particular sequence, I know I'm finding the sum of the first 30, so n here is 30. A1 is 1. R is 2. And I just go ahead and fill the information in. And then I'll put it all into a calculator. Remember to group so that when you plug it in correctly. I did it. You're going to get a very big number.
That's crazy.
Just put in $10 million on the 30th day?
No, he accumulated $10 million after the 30th day. So again, this is in cents, so if we change it to dollar form, it would be $10,737,418.23. Yeah, like this is assuming he had $10 million that he could spare, you know.
Why does he need to save money?
I mean, if
Because
he's,
that-
imagine.
Well, we don't know the problem here, okay? We don't know.
Why do you think he's
Imagine if I had interest going at the same time.
Well, over 30 days, that wouldn't be very much interest.
Okay, but if he kept that in there and he kept doing it.
Well, yeah, no, if he continued to do it, I wonder how much he'd have after like a year, 365 days. Your calculators would not be linking it, so we can't do it. But
That'd be a lot of money.
that would be so much.
I wish.
I love that. Okay. Any questions, concerns, or issues? Did anybody not get $1,073,741,823? Anybody confused by how we got that?
Are you gonna want it in dollars?
I would want it in dollars if I gave you cents as a unit. Yes, I would want it in dollars. Maybe like half or one.
Did you technically also divide it by 100?
Yeah, same thing. Dividing by 100 is the same as just moving the decimal 2 places to the left.
I want to make it something that does that.
Right. Okay.
Oh, yeah, interesting.
So now we're getting into the last piece of our notes, and that is the sum of an infinite sequence. This uses the formula S equals A1 over 1 minus R, where R is still our common ratio and A1 is still our first term. Notice that this uses an S with no other number attached to it, where our partial sum uses S with a number N attached to it. So make sure you can tell the difference.
That doesn't make any sense.
Why does not make any sense?
How is this a little bit confusing? Then only if it was like, why?
It's gonna work, I promise. Okay.
I think it's square.
Huh?
Are you sure? It's square.
No, I'm not forgetting a square. He is. I love it though. Love it.
If there was no square, how would we go in?
It's not going infinite. It's adding up all of the terms that follow that rule for an infinite number of terms.
If you add infinity, how can you get that?
Hold on, I'm gonna double check it because you're questioning me. Nope, I'm still right.
I'm not gonna say you're wrong.
I heard the saying.
I know. And then looking at it, it doesn't make sense, but it works. Okay. So what we're gonna do, obviously, is we're gonna do an example, and then we're gonna do an application example. So the first example asks us to find the sum of the following infinite geometric series. Again, this rule only works for an infinite geometric series, not an infinite arithmetic series. Notice I use the word series here instead of sequence, and you're going to see why in a second. The geometric series that it gave me is the summation of terms 1 through infinity of the sequence that follows the rule 3 times negative 2/3 to the n minus 1 power. A series is simply a sequence added together. Okay, so when you see series and you see sequence, they're pretty much the same thing. The only difference is the sequence has the terms separated by commas. A series has the terms put together with addition or subtraction.
Why? So they get a zero power.
Correct. Anything to the 0 power is 1. Because it says that you're taking that base and you're dividing it up into 0 groups, which means
That'd be zero.
we have no.
That'd be zero groups. Zero. How can there be no groups of one?
Conversation for another time.
Okay.
Yes, but remind me, and we will go into it. Okay. So looking at this,
Question.
it's fine. I love questions. I think they're fantastic.
You see what you're later.
Looking at this, what pieces of information do I need in order to complete this infinite sum? A1, awesome. And then what else?
A2.
Say it again.
A2. You find R that way.
I could find R that way, but doesn't it give me R?
That is pretty good. Oh, it's negative.
Negative 2/3 is my R here. So I need two things. I need A1 and I need R. This is an nth term rule for this given sequence. I know that because it has my rate or my ratio raised to an n minus 1 power.
So what did 3 just be?
So 3 would be my A1 and negative 2/3 would be my R. If you didn't know what R was from this, you could write out the first couple terms of the sequence and then you could use division to find your R, yes. But this one actually gave it to me. So then going from here, I just go ahead and plug it into that infinite sum formula, and I get S equals A1, which is 3, over 1 minus my R, which is negative 2/3. We go ahead and simplify this because I prefer a fraction if I can get it. 1 minus a negative 2/3 becomes 1 plus 2/3. To put my fractions together, I need to change 1 into a fraction with a denominator of 3, so it needs to change into 3/3. So when I put it together, I get 3 over 5/3. And then when we divide by a fraction, we flip it and multiply it into the top. So this becomes 3 over 1 times 3 over 5, which is 9 over 5.
Okay, how is that an infinite sum?
How is that? Well, if you actually saw what the sequence was here, it kind of oscillates back and forth. So it's not always just going to grow exponentially. Sometimes it will, and you're going to get a huge number. Sometimes it won't.
What did you do on the last?
So like no matter what you do to it, it's gonna add up to 9/5.
This one, yes. If I keep adding them infinitely.
Would it be like an asymptote then?
Huh?
Whack an asymptote.
Oh, yeah, because
Sometimes you would get like an
they'll be
infinity
negative
sometimes.
sometimes because it's a negative.
Also, when I take negative 2/3 to a power, I'm making it increasingly smaller. So when we add it, it looks like we're adding a bunch of numbers, but we're actually adding really small decimals together. That's why. How do we feel about this one?
Wait, did the last step you take the 3 on top? times the
Yeah, so
first
the
one?
3, I just made 3 over 1.
Okay.
And then this one I flipped and multiplied into the top. You could have left that as 3 times 3 over 5, but I do it over 1, so remember the numerator goes to the numerator and denominator goes to denominator. That's the hardest part of this one, I think.
Fist bumping.
Okay, how did we feel about this particular example?
She got you there.
Good? Okay, so we're gonna do an application example and then we are finished.
You're too strong. You're too strong. I'm never giving you this one again. It'll break my hand.
Yeah, big fist bumps is a very competition. Needs that.
I need it for the fist bump stuff. Just the fist bump.
Yeah, it's on the wrist. It's on the wrist. You can put it on the board.
It's not there. Is this the really short one or the really long one?
It's not even long.
So it's the long
That's the
one.
last one we're doing.
This is the last one.
I like your C on each. Yeah.
What? No,
Yeah,
that's
yeah.
not the C, it's connected with my A.
Okay.
Yeah.
Cursive.
You should see the H in my, it doesn't look like an H.
Fun people. Nice.
So the joke is.
Do we get our Sudokus?
Oh, shoot.
Psych, no, we don't.
I will print them, just stop by a different time during the day and get them. Preferably after lunch.
After lunch, we'll be gone.
Okay, I'll try to print them before then.
Just put them during this hour. 'Cause we're
Well,
having
I can try, yeah. Okay.
got like 30 minutes. Does it really take?
You don't have 30 minutes, but that's okay.
You're you know.
So the first thing I'm gonna do is I'm gonna draw a picture. We don't really need that one. Just so we can kind of visualize what's happening with this ball. So the first thing I know is that I dropped the ball from a height of 10 meters. So the initial travel distance was 10 from where I dropped it down to the ground. It says the rebounds at a specific ratio. What is that ratio?
1 to 2.
1/2. So that means if it dropped a distance of 10, it's going to rebound and bounce up a distance of 5 because 5 is half of 10. Of course, when it goes up, it must also come back down. So that means it's also traveling back down 5.
Oh, this is what you were drawing.
And then when it hits the ground, it bounces back up at half the height of the previous bounce. So this one will be 2.5. And then it has to go back down that same 2.5. And this pattern is going to continue to keep happening. And each time, the bounce back up is going to be half of the previous bounce back up. So what it's asking us to do is it is asking us to add up the total distance that this ball traveled for each bounce down and up added together over time. We're actually doing 2 infinite sums here. We are doing the infinite sum of all of the downward bounces and the infinite sum of all the upward bounces, and then we're going to add them together. So I want to go ahead and do the upward bounces first. So I put S of upward, so some of the upward bounces. Subward.
Definitely.
What words floated cousin?
Of course, I want to go ahead and write what the sequence looks like. That way I know that I'm starting with the correct values. So what was the first upward bounce distance that my ball traveled?
5.
5, right here. And then it went back down and it bounced up again. So what was the height the second time? 2.5. So each time, I'm just getting smaller by 1/2. So this is going to be the sum of all of those upward bounces. Knowing what my sequence looks like, I can go ahead and fill in the information to my infinite sum formula. Infinite sum is equal to my first term 5 over 1 minus my common difference, or my common ratio, I'm sorry. What's my common ratio for the sequence? 1/2. Because it's essentially dividing by 2 or multiplying by 1/2 every time it continues on. So then I just simplify this. 5 stays 5. 1 minus 1/2 is 1/2. We get a fraction in the denominator that we flip and multiply into the top, and it becomes 10 over 1, or just 10. I will go ahead and put a unit with this because I know that it's in meters. So that means in total, on all of the upward bounces, my ball traveled a total of 10 meters.
Couldn't you just add 10 to that and that would get your downward?
Yes, but we're going to do it the long way first. So now that we've calculated the upward distance, now let's calculate the downward distance. Again, I'm first going to write the sequence that we'll be following. So my first downward bounce was, or downward distance, sorry, 10. Second downward distance was 5. And then as the previous one, it also continued to just be cut in half on every downward bounce. I didn't call it a bounce, downward travel distance. I don't know.
Ollie?
There you go. Having this information, I go ahead and I create my infinite sum formula, which is again equal to my first term, which here is 10, divided by 1 minus my common ratio, which is 1/2. Yes.
If the sum is infinite, right?
Eventually the
Why?
ball's gonna stop moving. So we can get just a number. Well, I'm not sure it ever actually truly stops moving, but it'll be moving so smallly that it's uncountable. I don't do physics, so I don't know if it ever really stops moving.
Well, it'll stop bouncing up.
Right, right. So then we go ahead and work through this. 1 minus 1/2 is 1/2. Flip it and multiply into the top. And I get that the downward, distance traveled is 20 meters for this ball. So my total distance traveled is what? 10 plus 20, which equals 30 meters. And we are finished. So that is it for the notes for geometric sequences. You will have a test next week. Your review should be going up today. I'm almost finished with it. And you have all weekend to review it, or to do the review and to do the homework. Homework's due on Monday.
Is Monday a review day or test day?
Review day.